I'll begin with a prayer. Dear Father, we thank you for this day. Again, Lord, I thank you for the students for this semester that we're beginning. I just pray you bless this class. Help us to just think clearly and to glorify you, Lord, what we do, Lord. In your name I pray. Amen. All right, so as you guys know, we changed books. We are now in this book, although your copy might look different. Yeah, American copy is interesting. You guys are extravagant. If I were you, I would have one with a red cover from the Far East. The rest of you must be using PDFs, eh? No. International one, yeah. I know.
It's in my backpack.
It's fine. I'll stop harassing you guys. But yeah, it's a I love this book. Sometimes it's frustrating as a professor to try to teach out of this book, though, because there's just so much in every section. It's almost never going to be the case I say all of it in class. So that's so important for you guys to read along, right? So I will try to hit the important points today from section 3.1. We'll see where we get, okay? Just to give you a look ahead at what we're doing, first part of the course is going to be extension fields and the basic theory of extension fields, which is chapter 13 in Dumpment Foot. Then the second part of the course is going to be on Galois theory, roughly chapter 14 of Dumpment Foot, although we'll borrow some insights from some other sources. And then the third part of the course will be on modules, which is basically linear algebra over ring. So let's get started. So what's the characteristic of a field? Characteristic of a field is what I said last semester. Well, I think he tends to use this for the characteristic of a field. It's the smallest positive integer. And so for us, n is going to be 1, 2, 3, da-da-da in here. All right. Just to be clear, 0 is not in the natural numbers. Okay. It's going to be the smallest p such that what? P times the identity in the field, multiplicative identity obviously, is equal to 0, right? If it exists. And what's the characteristic of the field otherwise? Right. You can prove that those are the only two possibilities, all right? And the reason that those are the only two possibilities basically just stems from these rules here, right? M plus n times 1f is... Now, I don't think I ever actually proved these last semester, and I don't think I'm going to start this semester either, because actually he says it's easy. It's easy to... I would say it's tedious, I would say, is the better thing to say, to prove these rules directly from the definition. Now, I'm going to stop writing 1 sub f because it's getting really old already, and we'll just write 1. But proposition 1 was that the characteristic of f is either 0 or a prime, all right? So in fact, that positive integer p has to be a prime. Examples? What are some good examples of this? So I think we've already seen these last semesters, of course, but just get us started in here. 1, of course, the real numbers and the rational numbers. These are characteristic 0, right? 2, if we look at the, now here's half the reason I'm covering this example is just this notation. So this is a change in notation. Double blackboard f sub p. This is the finite field with p elements. We would have used the notation z sub p last semester, right? And that also for us would be... Now, I think part of the reason he's not using this notation anymore, and why some people wouldn't use this notation, right, is that this has a different meaning. And if you look at what's called p-adic analysis, uses with different meaning. So what I'm going to say then is that I'm going to try to make a habit this semester of not using this notation, and I will instead use f sub p for the finite field with p things, okay? Another example, which I don't think I did last semester, but we could have. We had all the tools we needed to do it, is if we look at the polynomials with finite field coefficients, all right? This is polynomials. Then if you look at, what would this mean? F sub p parentheses of x, what would this be? Yeah. Yeah, rational functions with coefficients where? From fp, right? And that's a field. If we do the field of fractions construction, like we covered last semester, right? That will create these, or at least something that's isomorphic to those, which then we can identify in a natural way with rational functions. Now we should have a little talk about. You can look at this from another perspective, which I think is worthwhile. If we look at a homomorphism, right? There's a natural homomorphism here, really. Phi from the integers to our field, right? And this is a ring homomorphism. Ooh, this marker is not going to live long. Ring homomorphism, and how are we going to define it? We'll say phi of n is equal to n times 1, right? Now, this is 1 plus 1 plus da 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 plus 1 n times, right? For what? For n in the natural numbers. But of course, you can extend this to integers by just adding together successive copies of -1 and so forth, right? That is the definition of the thing I wrote on the other board, right under the definition, right? And in fact, these properties are exactly what we need to get what? That phi is in fact a ring homomorphism, right? It preserves addition and multiplication. It sends 1 to 1. But there's more we can say. Let's see here. So here's a reminder, I suppose. Ideal in field is blank or blank. Can you fill in the blank field F? It's either 0 or the whole thing. Because, well, I don't want to get back into all that, but so if you look at this ring homomorphism, right, the kernel of the ring homomorphism is an ideal, right? Right, and well, also this is it's a subset of what? Subset of the integers, right? So what are the ideals there? Right, it's prime ideals. Well, it's either the whole integers, right, or nz, right? Well, I think we can have prime ideals. Huh. Right. Sorry, I'm getting to a point here. So if we look at what happens if we look at phi. With z mod kernel phi, this would be isomorphic to what? The image, right? Phi of f. I'm an idiot. Phi of what? Z. And that is itself a what? Yeah. Let's see here. gotten hung up in the logic here. Oh, I'm sorry, I'm an idiot. I'm trying to say something that I can't say. So, of course, this is the image, which is a subring, right? I know it's a subring because this map sends, I mean, this is actually a ring homomorphism in the sense of last semester. It sends the identity to the identity, right? And so this is a subring of F. It's a subring which is either isomorphic to what? You got two choices, right? It could be isomorphic to Z, right? If the kernel of phi is what? 0, right? Because Z mod 0 is Z, up to isomorphism. Or it could be isomorphic to Z mod PZ, right? If the kernel of phi is PZ. So what's the larger point here? The larger point is that every field contains a subring, right? Which is isomorphic to either what? It's either isomorphic to Z or Z mod PZ, right? But it's a field also, right? So if we take that subring, Z or Z mod PZ, both of which are integral domains, we can do the field of fractions technique, right? And that technique will produce a subset of the field in question F, which is naturally identified with either the rational numbers or the finite field with p elements, right? So this implies F has subfield, right? Isomorphic to either Q or FP. And again, that arrow is just the field of fractions technique applied to the subring, which is either the integers or, of course, the field of fractions technique applied to Z mod PZ is kind of boring. It doesn't produce anything new because everything in there except for 0 is already a unit, right? So the field of fractions is kind of a yawn for that one, but you can do it. And this is why we define the prime subfield. F has, let's see how to say it carefully, the prime subfield of a field of F is generated by 1 sub F, all right, and is isomorphic to either Q or FP. And when I say generated, I'm referring back to this whole thought process over here. That's not a technical sense of generation we've used before. But that brings us to probably my most important definition for today, which is extension field, which I also gave you guys last semester, but we should say it again and introduce some notation. What's an extension field? That's a specific concrete construction of an extension field. And almost every extension field we'll look at will have that form. So that's like a pretty good answer.
So it's a field that's a superset of an existing field.
Right. And I guess technically speaking, those, that's actually, you're getting ahead of the story a little bit, which is fine. Those fields we construct by polynomial quotients are actually isomorphic to, if you want to get really, really pedantic, you could insist that the extension field takes the given field as a subfield, as a literal subfield, as a subset of the given field. And if you're picky like that, then those things, yeah, the factor rings would actually just be extension fields of a field which is isomorphic to the given field. But this kind of distinction is one we don't want to make in here, actually. That's a damaging distinction to make. Like, we would like to identify isomorphic fields whenever we can. So, in fact, that's one of the main identifications that we kind of make a lot in here without saying, is we'll identify a field and a field which is isomorphic to that field by some natural construction.
I read that that's the kind of thing that is made explicit in type theory, that isomorphic things are considered equal, whereas in set theory you kind of have to do a bit of fiddling to a little bit less rigorous.
Yes, so to be careful, we'd have to get into foundations and type theory and, yeah. Yes. If K is a field containing the subfield, but I will leave that to graduate school for you guys. The subfield F, or if you wanted to, that talk I was talking about at the end of the semester, if you'd like to give a talk on type theory, you're welcome to. But I want to try to keep the talks in here more about topics that we just either tangentially touch or don't really get into. We'll talk more about the talk/paper and what you guys want it to be. Yeah. But of course, also I'm just trying to be lazy the last week of class, make you guys talk. Hey. Let's see here. Contains subfield F, then K is an extension field. All right. Of F. Denoted, and here's the main, half the reason I'm writing this out is just to say the notation K over F, right? So that means that K is an extension field of F. This is not a quotient ring or a factor ring, all right? So beware of this notation. It's not one we've used before, I don't think. And also this picture is going to be a big thing in here eventually. So this is the picture. It's a very, very short tower of fields. It's just two of them. Now, if you look at it, K has F as a subset, right? So that means that I can take any, if we let X and Y be in K, right? And if we let C be in F, then what's C times X plus Y? And what if I have C2 also in F? And what would be like C2 times X? And what would C plus C2 times X be? Right, so of course, F is a subset, right, of K. What'd I do? Exactly. So it's a field. It's a ring, right? So we have distributive, and we can do this. It's associative, the multiplication, right? But if you look at this, and of course we also have that one times X is X again, right? And et cetera, right? This tells me that K is an F vector space. So every extension field is naturally a vector space in the sense of linear algebra over the base field. So the field which is being extended is the base field. Nope, not necessarily the case. Like the real numbers are an extension of the real numbers, and they're a vector.
If it's a strict superset.
Yeah, if it's a strict superset, then it's got to be, I suppose it's got to be larger, yeah.
Right. So does that necessarily translate to a higher dimension, like
I believe so.
dimension one
Yeah.
extension field that's
Yeah, I don't think you can have a dimension 1 extension field, which is not just the field itself. Yeah. Now, on the flip side of things, the terminology extension field and base field is totally ambiguous. If you take a particular field, is it the base field? Is it the extension field? I don't know. It depends on context, right? If I take the reals, are the real numbers the base field or the extension field? Well, they can play either role, right? Because if you look at the real numbers as an example, we can put it here, right? And of course, we can look at the extension field of the reals, the complex numbers, right? Or we can look at R as a extension field of the rational numbers, right? And there are lots of other things you could put in here, right? Now, one of the things you can prove is that if you have a base field and you look at extensions over it, then they all have the same characteristic, which means then that they all have the same prime subfield. So if you find the rational numbers at the base of some tower of fields, then you're looking at a bunch of fields that all have characteristic 0. On the other hand, if the primordial, so to speak, oh, wait a minute, I shouldn't use that terminology in here. The base field, f sub p, is what, then you're looking at a characteristic p. Yeah.
So the complexes would be dimension 2 over the reals, right?
Right.
What dimension would the reals be over the rationals? Would that be infinite dimension?
Indeed, the reals over the rationals are infinite. And that actually is our next definition. Way ahead of me. Ah! Oh no. Oopsie. So definition, the degree of k over f is denoted by this thing again. So it's like that. What do we use this for the index in group theory, right? So we're giving it a new meaning now. And it actually is, honest goodness, vector space dimension of k over f. And then, so if this is if finite, then k is finite extension. If this is infinite, then k is an infinite extension of f. Now, actually, I haven't seen that terminology, infinite extension of f, that much. I mostly see people say it's not a finite extension. Sorry. Now, Theorem 3, which I should write since I have been jibber-jabbering about too many things that don't matter today. Theorem 3. And again, just to remind you guys, section 13.1, thumb it and foot, right? Theorem 3 says the following. Let f be a field, all right? And p of x in fx polynomials over f, an irreducible polynomial. Then there exists field k containing, and so here's the thing I was talking to you about 10 minutes ago or so, Sam. It contains a field f prime, which is isomorphic to f. Right? It contains an isomorphic subfield, right? And in which p of x has a root. What's that mean? That means p of alpha equals to 0 for some alpha in k. And that p of alpha, I mean, there's a lot going on here. That's not the original polynomial. That is the natural corresponding polynomial over f prime. Yeah. Now, the proof is given on page 512 to 513. Since I talked so much about uninteresting today, I don't have time for the proof, but I will go on because the proof is pretty elementary. And I might have done it last semester. Maybe not, I don't know. Ooh, yeah, I had a feeling that red marker was going to do this. Oh, goodness gracious. Whoa, look at that. It's thick. Yeah. All right, so Theorem 4 we use a lot. Theorem 4 is actually kind of bread and butter calculationally for this chapter. It says the following. If we have p of x in polynomials over a field, right, irreducible, so the p of x is irreducible polynomial of degree n over f, and if we have k is that quotient you want to look at, Sam, f of x mod the ideal generated by p of x. If we let theta equal to x mod p of x, so this must be his notation for working in a factor ring. So I think last semester I would have written something like x equals, theta equals to x plus the ideal generated by p of x. Right, like I think this would be for us x plus p of x last semester. Okay. Then 1 theta squared, theta to the n minus 1 is basis for k over f. Right. In other words, we have k is equal to the set a naught plus a1 theta plus plus a n minus 1 theta to the n minus 1, where the coefficients a0 through a n minus 1 are in the field, right? So just to, I mean, this is all polynomials in, you could say, f theta, right, with degree less than n. It's completely arbitrary polynomials of degree less than n. There's no restriction whatsoever on those, right? And of course, what can we write here? What's the dimension of over f of k, right, is equal to n, since that's a basis, and of course that's also our new notation, right? Yeah. So let me, the proof, all right, the proof of this is essentially the division algorithm, all right? If you look at a polynomial If you look at polynomial in K, which is that quotient, right? You can write it, the representative, as a multiple of P plus a remainder term, where the remainder term has degree less than n. All right? And that's arbitrary. So the multiple of P goes to 0, and you're left with the remainder term, which ranges over constants all the way up through n minus 1 order things. And with our notation, that's just this. So that's essentially the argument. Now, to be more careful, and he does, he shows that it spans, right? Which is almost just what I just said. And then linear independence, you also need linear independence of 1 theta to theta n minus 1. If you assume that there was a linear dependence, right? Let's look at that part of the proof. Suppose there was a linear dependence of the thetas. What would that say?
Why do you get some linear combination that's not equal to 0 but has no difference?
Right. So that would mean that we had something like, C0 plus C1 theta plus Cn minus 1 theta to the n minus 1 equal to 0, where these are not all 0, right? But then what can you do? You can let g of x, right, equal to C0 plus C1x plus, shush. Let's see here. Oh, that's wrong. It's like actually A58. Okay. So if you let g of x be that, right, then what can you say about that particular polynomial? Oh, and you said it's, well, I mean that's just like by there's nothing. That's not what you're saying. You're saying something more interesting. We have that g of x is an element of this guy, right? How do you know that?
You have theta as a root, and actually theta is just x plus the ideal px.
Right.
So when you sum it up, it is equal to 0, which is the ideal px.
Okay. Right. Depends on what level you want to argue at. I think what you're doing is fine. But we can also see that from just going back to work, translate all the statements into statements about polynomials over the field, do the division algorithm for things over fx, and argue concretely there if you're not comfortable with what King was just saying. But one way or the other, we should come to the conclusion that g of x is a multiple of p of x. Yeah. What would that say?
So it has to be a multiple of px, but I mean, it's not possible because the degree of g is less than n, less than p.
Oh, right, exactly. So g of x, and that's exactly the contradiction. G of x is equal to some constant polynomial, not constant polynomial, just some polynomial, k of x times p of x, right? I mean, this is the set of all polynomial multiples of p of x, right? And that's impossible because g of x has degree n minus 1, whereas p of x has degree n. There's no way you can get back to n minus 1 from in an ideal which has, at smallest degree n. So that's a contradiction. Now, if you didn't believe what I just said, I would encourage you to go methodically and carefully read through the proof on page 513 to 514. All right. I will not prove everything in here, but I will try to do a slightly better job than I'm doing at the moment. Now, there are 7 examples in the section, all right, of different examples of this, and I think they're all great. The one that's kind of surprising is example 7, where he looks at rational functions over a field K, and he mentions that p of x equals to x squared minus t is irreducible. Rational functions in the variable t. Like, I think all the examples except for example 7 we have seen in 421, which is not to say I won't say them again in here. I just a little bit short on time today. Oh, come on. But that example 7 is kind of interesting in the sense that he uses Eisenstein to claim irreducibility of p of x is x squared minus t, right? Now, if you look at this, this would not fit under the Eisenstein criterion that we talked about last semester, right? But if you go back to page 509 in Dummett and Foote, you'll find on page 510 he gives a completely good proof for Eisenstein over essentially arbitrary rings. And that's one of the reasons that we really like this book, is he has a habit of going and doing things as generally as they can be done if it's not too much trouble. And that's a great example of that. I would encourage you to read the new, improved, extended Eisenstein criteria that we have now to work with. So we can check irreducibility in a more general context. Now, so I guess I should at least write down, the quintessential example, really, right, is r of x mod the ideal generated by x squared plus 1, right? So by this theorem, this should be isomorphic to what? A plus b theta, such that a and b are real numbers, right? Now there's a corollary 5 to theorem 4, which basically tells you how you calculate. And how do you calculate in this quotient? It's pretty simple. The quotient is set up so that p of theta is 0, right? So basically corollary 5, to summarize it, p of theta is 0. That's not actually what corollary 5. Corollary 5 says you look at the remainder, blah, blah, blah. It's more technical. But after the dust settles, we're just going to be saying p of theta is 0. So in this construction over here, p of theta is what? Theta squared plus 1, right? So to say that's equal to 0 is to say that theta squared is minus 1, right? Which is to, give a construction of the complex number system as a quotient of polynomial rings. Okay. Now, example 5 is interesting. He gets you thinking about how we could use the characteristic polynomial. I guess we haven't called it that yet, but this polynomial p to find the inverse of theta, right? You can just factor the theta out and solve for the coefficient will be theta inverse. So that's kind of sneaky. All right, so my last big idea for today is the notion. So this right here, we could also say that this is r of theta, right? And definition, if k is extension of f containing alpha, beta, and so forth, some collection of elements of k, right? Well, I'm just saying that suppose that k is a field which contains, it's an extension of the field f, and it also contains these elements alpha, beta, so forth and so on. Then the smallest field containing both alpha, beta, and so forth and so on, and f is f of alpha, comma, beta, comma, dot, 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 dot. This is the extension of f by alpha and beta and so forth. You can either adjoin a finite number of things or an infinite number of things, right? You can do this in an arbitrary collection, all right? But the most important case for us when just adjoin alpha, then we have f of alpha is a simple extension. All right, simple extension. With primitive element what? I think it's primitive element alpha, right? So one of the major results we'll find our way to in the next lecture or two is that any finite extension of a field is in fact a simple extension, which is kind of interesting, right? So if I take, for example, Q, and I adjoin square root of 2 and square root of 3 to it, well, that's also the same as Q adjoin something, right? So the next lecture, section 13.2, is all about how to look extensions with more than one thing, right? And the final theorem in section 13.1 is actually really important to chapter 14. Actually, it's theorem 6 and really 8. 8 is the one we use in Galois theory a lot, but I guess I'll talk about theorem 6 and 8 next time. I thought I was going to be like a page into the next section, and here I am, a page from finishing this section. I guess it's just par for the course. But I think I'm out of time, right? So I'll shut up.